Hey everyone, in Physics 40S class, Dr. Carroll here. This is going to be a short presentation to help you do well on Friday's test. Remember, it's a take-home test on Friday, so I'll send it to you through EDSB and or Gmail. Look both ways before crossing the street, and then you will send it to me as one file on Monday, April 4th. Monday, April 6th. So what are some equations that are going to be useful? Well, first, we're talking about linear momentum, so P equals mv, right? Remember, they're vectors, so linear momentum P equals mass times velocity. And so, for example, if I said calculate the momentum of a 200-gram butterfly moving at 4 meters per second, your P would be, well, you got to convert to kilograms, so 0.2 kilograms times 4 meters per second, which is 0.8 kilogram meters per second. Okay, so be careful with the units there. Then we looked at impulse. And so your impulse, capital J, equals F delta T. Yeah, it's a vector, that's true. Equals m delta v. Okay, so that's an important equation. In your mini text, it's on page 278. Okay, and so what kind of questions could that be? Let's say you're golfing and you hit the ball off the tee. So when it sits on the tee, v1 is 0 meters per second, and then it zooms off the tee at, let's say, 30 meters per second. For me, it would also be 0 meters per second because I would miss the golf ball altogether and it would just stay on the tee. And there would be no impulse. If you don't connect with the object, you don't impart an impulse onto the object, you don't cause a change in momentum. But here we did, so this is a better golfer than I am. And let's say the mass of the golf ball is 26 grams. So we want to get the impulse. So J, well, which one I'll use? I'll use the m delta v, but of course I have to convert to kilograms, so 0.026 times 30 minus 0. So you think I can do that in my head? 0.026 times 30 is 0.78 kilograms meters per second. You could also write it as newtons times seconds. Those are the same kind of units. Okay, let's do a stopping time example. Let's say, where I've lost the, there we go. Okay, let's say someone's falling from the sky. They have a parachute, luckily, and you want to get the magnitude of the impact force. So let's say the mass is 42 kilograms for the person falling, and they're falling at 9 meters per second, and then they stop when they hit the ground, and so the final speed there is 0 meters per second, and you want that because you want to get the impact force on that. Let's say it took 0.04 seconds. So F delta T equals m delta V, so F is m delta V over delta T. And of course, the shorter the impact force, the smaller the value of the time, that's what I mean, then the greater force, and that's going to hurt your knees. So it's 42 times 0 minus 9 divided by 0.04. And if you want to pause this video now and punch it out yourself, go ahead. I'm doing it live. 42 times 9 divided by 0.04, 9450. We'll put negative I just took the stylus onto the trackpad. That was funny. 9450. What are the units? What are the units? Newtons, right. Okay, that just means that you're directed in the opposite direction. The force up on there. So, there's a few other variations. I'm not going to do every single kind of impulse questions, but you'll be dealing with things like that. Okay, let's go to a new page here, and I'll go to 11.33. That's the good size here. And so the remainder is really on conservation of momentum. Okay, so let's say we're having two bodies and like recoil kind of questions. Then in one dimension, m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. Okay, so those are that is your one dimensional kind of question. So let's say we had one where a recoil one. Let's say you had a satellite in space and its mass of the satellite was 480 kilograms, and then you shoot off, let's say, 20 kilogram chunk at 10 meters per second. You want to calculate the recoil velocity of the remaining portion, assuming the initial satellite velocity is 0. So you take that as your starting point. So the whole initial momentum is 0 because the satellite's not moving. Then after, well, let's see, what did I say the chunk was? 20 kilograms. So you're going to be left with 460 is going to be the majority of the satellite hurling one way, V1 final, plus maybe it's some sort of payload or something, 20, oops, and those things come every now and then, times V2 final, let's say that's 20 meters per second. Okay, so then my V1 final would be 20 times 20 divided by minus 460. 20 times 20 divided by 460, and I get minus 0.87 meters per second. So the smaller object, which is shot off from the satellite, is traveling a lot faster. The bigger object, which is the vast majority of the satellite, once that little bit is gone, is traveling slower. But the momenta are the same, and that's what we mean by conservation of linear momentum. You can also do one with trains coming together, and we've done one like those. So just refer that, because you'll see some with trains coupled together. And then we had two-dimensional one, and there'll be a curling one. I'm not going to do another one here, but there are some curling questions which are glancing collision. I won't do the three-dimensional chocolate explosion one. And now that I say it, I never did a three-dimensional chocolate explosion one. I did a two-dimensional one, but it was into 3 fragments. But we're going to do a curling question as you see in our mini text. So that is the outline of it all. And remember, when you write neatly the answers in the spaces in each question, you take pictures using Microsoft Lens and then bundle it up into a PDF file and send it to me. Okay, so if you want more practice, just go on to the Unit 4 worksheet baritone, try some of those out, and other ones within that worksheet package to become a, dare I say it, superstar of momenta. Okay, you get a t-shirt that says that. Okay, have fun. I have to figure out, how do I stop the recording? It's going on forever. Recording, stop.